The principle of photocatalysis was discovered in Japan in 1967 by Professor Akira Fujishima. The phenomena can simply be described by the process of light speeding up a chemical reaction. Photocatalysts are materials that under light energy decompose harmful substances. Titanium dioxide, an N-type semiconductor, is the most commonly used one. When light energy from sunlight or fluorescent light is irradiated onto the titanium dioxide, decomposition on the surface occurs by the release of electrons. The released electrons bind with oxygen and form superoxide anions. The resulting positively charged surface pulls electrons from moisture in the air. The once water becomes hydroxyl radicals. Both the superoxide anions and hydroxyl radicals are extremely reactive. They decompose organic compounds such as oils, bacteria, hazardous gases, fungus, and stain-causing odors. They are turned into harmless products such as water and carbon dioxide. This is a near-permanent effect. The driving force behind photocatalysis is the excitation of the electron and hole pair. This is why the photocatalysis effect is limited to semiconductors. A band gap is necessary to create the electron-hole pairing. As for the type of semiconductors, N-types dominate the category because electrons must first be donated in order to combine with the water in the air.
In order to harness the useful qualities of photocatalysts, it's necessary to understand what factors contribute to their effectiveness. Seeing as that photocatalysts are mainly semiconductors, it follows that one of their main limiting factors is the wavelength of the incident radiation and the photocatalysts' ability to absorb it. A material's quantum efficiency is a property which measures how good a photocatalyst is at absorbing light across the broad electromagnetic spectrum. If a light is only active within a narrow band of EM radiation, it has a low quantum efficiency. Mass implementation of photocatalysts would require the use of solar radiation as the excitation radiation source. However, solar radiation is mostly visible and infrared radiation with very little high-energy ultraviolet light. This is an issue since most high-efficiency photocatalysts are only active under UV light, rendering them impractical for general use in our solar system. However, materials like titanium dioxide can have their quantum efficiencies increased via doping with carbon. The addition of carbon adjusts the band gap of the material, allowing it to excite a greater fraction of electrons to the conduction band under a given stimulus. Dopants can improve the photocatalytic activity of materials by reshaping their crystallographic topography as well. For example, by doping sodium tantalate with lanthanum, a step surface geometry is created, which prevents the recombination of electron-hole pairs, extending the active lifetime of this photocatalyst. Similarly, by varying the composition of lead zirconate titanate, or PZT, a large spike in photocatalytic activity can be observed at the morphotropic phase boundary at approximately 48% titanium, which is a compositional region in which tetragonal and orthorhombic phase PZT can coexist.
The applications for photocatalysts are numerous. They include water and air treatment, photocatalytic water splitting, synthesis of organic compounds, self-sterilization of medical equipment, self-cleaning of structures and buildings, and more. Two applications that we will focus on now are the synthesis of ammonia and self-cleaning coatings on structures. The synthesis of ammonia will be focused on because it is a particularly difficult compound to synthesize, but it plays an important role in today as it is a common fertilizer in a growing population. At room temperature, the enthalpy of formation for dinitrogen to ammonia is negative. This means the reaction is not possible under ambient conditions. This is where photocatalysts are useful. Understanding the workings of photocatalysts is useful to understanding how they come into use. As described earlier, electrons are excited by the energy from light. These excited electrons can move to the surface of the photocatalyst and interact with dioxygen to make a superoxide anion. This formation leaves the surface of the photocatalyst positively charged. In the synthesis of ammonia, this behavior is needed as the charge left on the surface allows the surface to interact with water. Through subsequent reactions, dinitrogen can be reduced to ammonia. A few things to note are the need to use a photocatalyst that has a small band gap in order to satisfy the thermodynamic reduction potential for dinitrogen to ammonia. Also, to keep yield as high as possible, it should be a focus to keep electrons from recombining with their vacancies. Another use for photocatalysts is self-cleaning films on buildings. Buildings can be sprayed with a thin layer of photocatalysts such as titanium dioxide. Pollutants in the air such as car exhaust, grime, and general pollution adhere to the building regardless of it having photocatalyst coating or not. With the photocatalyst on the building, the oxidation power of the surface is very high, as described earlier. This high oxidation power decomposes pollutants and they simply wash away with rain, keeping the building looking new for years. The limitations of photocatalysts vary per usage, but there are some general concerns. One limitation is the light required to activate the photocatalyst. Sometimes it may not be visible light that activates the photocatalyst. Also, depending on the use, such as in forming ammonia, the yield may be very low with current advances in photocatalysis. Another limitation may be materials used. Sometimes materials may pose health threats or simply not be cost effective. Overall, photocatalysts are a promising category of materials that can reach a variety of applications with the right research. In the future, photocatalysts could be solutions for many of the problems we face today, from energy storage to managing pollution to providing food.